Hello. No, wow, questions. Loads of them. I've been good, thank you. Um, one, two, three, four in the year seven. Well, yes, I will start with the year seven booklet, which I think will repeat a lot of questions across the three booklets. It's quite a difficult topic, this, so I'm going to be as helpful as I can be with regards to this one. So let's talk about some of these questions. Right. Read the information. I mean, no, I might have to get another pen. Read the information about car engines. Burning petrol in air is an exothermic reaction. Just to be clear, exothermic reactions are ones that release energy. Usually, the best way to imagine that is a fire, right? A fire is burning, and therefore we have an exothermic reaction. This is used in car engines. When petrol burns, it produces harmful substances, nitrogen oxides and carbon monoxide. Drawing, the exothermic reaction makes the temperature, as I said, if you remember, exothermic is like having a fire. What does that do to the temperature? Increases it. And that is because in exothermic reactions, energy is given out to the surroundings. Um, okay, the equation is here. Which one is a compound? A compound is when you've got two or more elements joined together. So isn't it this bit over here? So you can write just NO, or you can write 2NO, or yeah, so that's it. You want the formula, so you have to say either that or without the two at the beginning. The equation is that why is it important to stop carbon monoxide? So carbon monoxide is a poisonous gas. When we breathe it in, it can be bad. It can affect how well we breathe. So that's it. We don't want carbon monoxide released into the air because it is poisonous to us. Um, right, then catalyst. So a catalyst, the definition of a catalyst is that it speeds up a chemical reaction. Okay, that's a tick. That's what a catalyst is. Um, the other part of the definition is that it's not used up in a chemical reaction. So you don't use it up. You can use it again, basically. And so that's not the answer. You don't put a tick because it's not used up. It says here that it does not change the rate, but it does change the rate. So that's not the answer. That's not the answer. Different reactions do need different catalysts, so that is the tick for that one. Um, 1, 2, 3, 4, 8. Okay, and then keep going. All right. I mean, you could have got this without really knowing this. You wouldn't have done this in the lesson. But if I said to something is nano-sized, what does that suggest it is? It suggests it's very small. Smaller than normal if it's nano-sized. Um, Catalysts contain platinum, so that's why a manufacturer of catalyst would want to use less catalyst. Probably because platinum sounds expensive. Let me see what the answer is. Yeah. So the answer to the question is that it would be cheaper. Okay. Right. One, two. I'll get to the booklet three one after these few questions. 1, 2, 3, 4, 8. And you said 1C, which is done. 1, 2. A student investigating the energy change occurring in the endothermic reaction between potassium hydrogen. Okay. Right, quite a complicated question. But if I was trying to measure the amount of a liquid, you will have one of these things in your kitchen, I suspect. Um, and it's basically a measuring cylinder. That's how you use a measuring cylinder to measure the amount, the volume of a liquid. Um, Right. The student used a glass beaker. Right. Let me explain this. Quite a difficult question, this. In fact, this whole booklet is quite complicated, so I'm happy to do most of it. But if you are doing an experiment in which you are going to measure temperature, so you want to see while you're doing what's going on in here, how the temperature changes. Does it get hotter? Does it get colder? The problem with using a glass beaker is that glass is a very good conductor of heat. That's why you don't have hot drinks out of glasses, because if you put your hand on it, then all the heat comes out to your hand. So if we use a glass beaker, a lot of the heat goes out that way, meaning that the thermometer doesn't pick up the heat. So you don't actually measure it properly. So using a glass beaker is not great. Instead, what you should use is a bit like the things we drink coffee out of. They're called polystyrene cups. So use a polystyrene cup to improve this reaction as it, I want to say, insulates heat, um, or is a better insulator. Insulator means it keeps the heat in. That's why your coffee stays warmer. And so if you're measuring temperature, you kind of want to do that. Um, five, six, and seven. Yeah, I'm getting through most of booklet one, basically. One, two, three, four. Oh, God, I'm not doing the whole thing here. Five, six, and seven. Right, okay. I'm just doing the whole thing. Which two variables should keep the student keep the same to make this a fair test? Right. If we are investigating the energy change when we're doing this, right, reacting these together, and we're trying different amounts of this thing here, then what we should do is keep the amount of the other thing, the acid, the same. That's what we should do. That's there. And we should probably try to keep the starting temperature the same. If we're measuring temperature, then we want to try and keep the beginning temperature the same, and then we'll see how much it changes. This is reading off this. I'm not going to answer this question because you should be able to do that. Range just means from the lowest to the highest. So from 15.8 to 16.1. And then calculate the mean. Again, I'm not going to do this for you. I'm going to tell you that to calculate the mean in maths of three numbers, you add them together and then divide the answer by how many there are, in this case, three. So add up those three numbers and divide by three. Um, I'll come to that question about hydrogen and oxygen, and I'll also come to booklet two just after this, and then booklet three, okay? How do the results show the reaction is endothermic? Don't know. Uh, is it that the temperature has gone down? Yes. It's because the temperature, does it tell you what we started with? Uh, oh, I see. So at the beginning, it was this number here, 21 point something, whatever that is. I don't know if that's the answer. But what's happened here is that over time, the temperature has decreased. So an exothermic reaction is when we give out heat, so things get hotter. If things get colder, look at the temperature, it's gone down, the number, then it's an endothermic reaction. So the results show that the temperature has decreased. Um, so draw two straight lines of best fit. So when you have, so there's one, and then there's the other. That's the two lines that we want here. Describe how the lowest temperature changes as the mass of potassium hydrogen carbonate added increases. So you want to say between 1 and 5 grams, um, the lowest temperature decreases. You see that bit of the graph is going down. But then after 5, what happens? It stays, there's no change after that. So when you have a straight flat line, the temperature is not changing. You see that? It's staying the same. So after 5, there is no change. It takes a bit of practice to get used to reading these graphs, okay? It takes a bit of time, so don't worry. Um, um, I okay, I'm getting through those, yeah. After 5 grams, there is no change. Okay, right, so that's answered one of the other questions. I think people have just asked me this whole booklet, haven't they? Three, four, okay. Instant cold packs are used to treat injuries. One type of cold pack has a plastic bag containing water. Inside this bag is a smaller bag containing ammonium nitrate. The outer bag is squeezed, so the inner bag bursts. The pack is shaken, quickly gets very cold. Um, why does the bag get cold? The reason the bag gets cold is because heat energy is taken in from the surroundings. So it's quite hard to explain that, but it's essentially an endothermic reaction is one that sucks in heat. So that means around it, it gets colder, just like in an exothermic reaction. If I start a fire, that's an exothermic reaction. It warms up everything. If things get cold, it is because it's an endothermic reaction. It takes a little while to get your head around that. Um, Yep, I'm going to get to booklet three. Well, just give me a moment. Draw a ring around the word the better weather. Change when it dissolves in water. It has to be endothermic. As I said, if something's getting cold, it is an endothermic reaction. Explain why the pack is shaken after the inner bag has burst. So the reasons we want to shake this is because it's a bit like we want when you shake something, you get a faster reaction. Okay, so you want to say that you want to get a faster reaction, um, and I'm going to put a technical thing in here by getting more collisions. So you may have learned during your lesson about collisions. So when particles hit each other, that's when they react. So by shaking it, you're trying to make them hit each other more. It's called collisions. This shows magnesium burning in air. How can you tell a chemical reaction is taking place? Well, I mean, probably just the flame, right? So you get these flames and stuff when a chemical reaction is taking place. So I think that would be that. Name the product from the reaction. I'll just tell you. When you're burning something in air, what you are doing is adding oxygen. So if it's magnesium to which you are adding oxygen, what gets made is called magnesium oxide. Okay. Um, the magnesium needed heating before it would react. What conclusion can you draw from this? Okay, so I explained this to the people I taught a little bit, but when you do a chemical reaction, right? Imagine a matchstick. I like to use a matchstick as my explanation here. Okay. In a matchstick, there is a fuel in that red bit, and there is lots of oxygen. Now, you get fire when the fuel reacts with the oxygen. The problem is, if burning is when fuel and oxygen hit each other, then this should be on fire all the time. But you know that a match isn't on fire all the time. You have to do something to make it catch fire. You have to strike it on the side of the box. When you strike it on the side of the box, what you're doing is for a while making this really hot. And when these particles are really hot, let's make them red to show that they're hot. Okay, they fly around faster, right? They're going faster. And if they hit this harder now with enough energy, you get the fire. That's what you're doing, right? And that energy, the extra energy that you need during a chemical reaction, is called the activation energy. Okay. I'm just getting through booklet one, then I will move to booklet two, then I'll move to booklet three. Okay. So a sample of the product was added to water and shaken universally. I'm not going to do this question. I want to let you try and do the universal indicator question yourself. And I'll do this one because you won't know this, but a nanoparticle has a high surface area to volume ratio. And then you won't know any of this, but I shall just tell you the answers. Um, we use the nanoparticles in sun cream. What do you want a sun cream to do? You want to cover your skin better, right? And so what these little particles do is they give you better coverage. The disadvantage of using nanoparticles is that they can damage cells. Again, you wouldn't have done this, so don't worry. Right. Oof, okay. If I said to you that this number is 10 and this number is 2, and I said to you, how many times bigger is this number than this number, then you would do 10 divided by 2. It's 5 times bigger, right? So when a question says how many times bigger is this number than this number, you need to just do this number divided by this number, which is easier said than done. But on my calculator, I will do 1 times 10 to the power minus 6. And on the bottom, 1 divide by 1.6 times 10 to the power minus 9. And whatever the calculator says is the answer. 625. 625 times bigger. Right. Choose words to complete the sentences. In air, the two most common gases are, surprisingly, oxygen and nitrogen. When natural gas burns, energy is released mainly as heat. When you burn things, it's mainly heat energy. When natural gas burns, a gas is produced which turns lime water milky. Some of you may know this, some of you may not, but it is. I've got it. I'm getting to booklet two after this one, if that's all right. So I want to get this booklet done, then I'll move to booklet two. So the gas is carbon dioxide. Okay. Um, Wax is a fuel. I'm not going to write the answer to that one. The wax, why does the wax disappear as it burns? So when you burn a candle, why does it get smaller over time? Um, Surely it's because it is giving off smoke, right? It's giving off gases. You can see it when you burn a candle. You can see the gas being given off. That's what the wax is turning into. Okay. So you can say the smoke is being given off. Smoke or gases. Okay. Right. This question. Ooh, that's interesting. Right. Draw a ring around the correct mass of oxygen, and then draw around the number of atoms. Okay. So there needs to be a number in this box that when you add these to it, you get 101. So you could do, on your calculator, 101, take away 39, take away 14, which is 48. So 48 goes there, but then you need to go, how many atoms is that? So how many times does 16 go into 48? It is 3. So there's 3 of those, 16 each makes 48. Okay, you can circle the correct numbers there. What does exothermic mean? Exothermic, I'll just say it. It is when energy is given out to the surroundings. Um, which explains why carbon dioxide is a gas at room temperature. You will have done this in theory in an earlier chemistry topic. But it has a low boiling point and it's made of small molecules. That's what carbon dioxide. That's why it's a gas at room temperature. Um, If you wanted to find out that a reaction is exothermic, in other words, it's given off heat, surely what you need to do is measure the temperature before and measure the temperature after. And if it's gone up, then it's exothermic. And that's the answer to part two. How would these measurements show the reaction is exothermic? The temperature would have increased, right? Exothermic reactions, it gets hotter. A student investigated how changing the concentration of the acid affects this reaction. Each taking a different concentration of hydrochloric acid. A control, you again, this would be hard for you, but the volume of the acid probably needs to stay the same. Also, you probably could put temperature as the answer to this question as well. Which test tube create the greatest concentration? The bigger the concentration of an acid, the faster it reacts. How do you see a faster reaction in these test tubes? You'll see more bubbles. And so test tube B should be the answer to that question. Why did you use a test tube? I just told you. And the student predicted that if the temperature of the acid was increased, the reaction would take place faster. Why? When you increase the temperature of a reaction, the particles move faster because they've got more energy. And because they've got more energy and they're moving faster, they collide more often. There's more hits. And the more hits you have, the faster the reaction goes. And that completes that. 3E, booklet 2, and then somebody else has also asked me 3 and 4. So 3 and 4. It's 3 on. There it is. What does exothermic mean? It is when heat is released to the surroundings. Which is an exothermic reaction? You should have had this in your notes. In fact, I shouldn't even answer this. I'm not going to answer it because you should have it in your notes. C. Calculate the, again, you would have done this in an earlier topic, the percentage of oxygen in carbon dioxide. Okay, so what you need to do is work out the relative mass of carbon dioxide, which is carbon, which is worth 12, plus 2 oxygens, which are worth 32. 12 plus 32 is 48. That is the total mass of carbon dioxide. Then what you need to divide that by is how much of that came from oxygen. So out of that 48, All of this came from oxygen, which is 32. 32 out of 48 is the fraction of oxygen in carbon dioxide. To turn into a percentage, we times by 100. It's like you getting 32 out of 48 in a test. And I said to you, what's that as a percentage? You would times the fraction by 100 and you would get 66, 67%. 67 should be fine. Balance the chemical equation. I'll just tell you this again. We probably haven't done that much balancing really with everybody. Do I need to balance this? Two. I'm going to put a 2 there and a 2 there, and I'll explain why. On this side of the equation, there are two hydrogens that we have doubled. So there are now four hydrogens. And we have doubled that oxygen, that's two, plus these two makes four. So there's four oxygens as well. On this side, we had two hydrogens that we doubled. So we've now got four hydrogens, so it's the same. And we doubled these two oxygens, so the oxygen was four as well. It's balanced if there's the same number of each thing on both sides. Um, right. Oh man. 6.8 grams of hydrogen peroxide decomposed with the answer's 36. Right. What it tells you in this question is that if I had 6.8 grams of this stuff, I would make 3.6 grams of water. Now what we're doing is making it 68. So we're making this number 10 times bigger. If I make that 10 times bigger, I should make 10 times as much water. But is it water? Oh, wait a minute. Let me do this again. Wait, do that again. Sorry. Okay, right. Let me write this again. So we have in this equation, it's not 36. This stuff making water there and oxygen. We have been told that if we have 6.8 grams of this, we make 3.6 grams of water. Now, masses in chemistry should all add up on both sides. So if I've got 6 grams that I start with, I should finish with 6.8. So 3.6 plus something should make 6.8. 3.2. Now what we're saying is we're going to start with 68 grams of this. If I've got 68 grams of this, then everything gets 10 times bigger, and it should still add up. And the question is, what's the mass of oxygen produced? That's there. Okay, so that was 3, and then something else to do 4, and that was it before I move on to booklet 3. A student investigates the energy released when zinc reacts with copper sulfate. Okay, so we followed a process, and it tells you how we did it. We basically put some stuff in, and we measured how hot it got. It started at 21, it finished at 32. Lovely. It got hotter. Calculate the change in temperature. I'm not going to answer that question. Calculate the energy. Oh, I've got to answer that question. I don't need to do this. Right. So I'm going to tell you how to do it. I'm not going to do it. The change in temperature is the difference between these two numbers. Okay. Right. And then it says calculate the energy released. And it tells you how to do it. It says the volume of solution in centimeters cubed. So we need to just go back and find where it says that. It says the volume of solution is 100. See that? 100. So I want to take that 100 from here. Multiplied by 4.2 times the temperature change. The temperature change will be whatever answer you get there. And then you put this into the calculator and you should be celebrating. How can you tell the reaction is exothermic? If the temperature has increased, it is an exothermic reaction. And again, how can you tell from this diagram that the reaction is exothermic? Right, there are two types of these diagrams. Either one that looks like this, or one that looks like this. In other words, in one of them, the amount of energy, this is energy, that we begin with is higher than the amount of energy we finish with. See how we've gone down there to finish. Whereas in the other one, the amount of energy we start with is lower than the amount of energy we've added energy. If we increase in energy, it is an endothermic reaction. If we decrease or lose energy, it is an exothermic reaction. That energy is the fire that you get in an exothermic reaction. So how can you tell from the energy diagram that the reaction is exothermic? What you need to explain here in words is that the energy of the products is less than, so it's lower than, you see it's lower, less than the energy of the reactants, which is what we started with. Was the answer 3E 12 grams? No, it wasn't. It was 32. Which arrow shows the activation energy? The activation energy is always the amount from where we begin to the highest point. Because, as I said with that striking the match example, in any chemical reaction, we often have to increase the energy to begin with to make it start. And that's the increase. You see how it's gone up? We have to make it go up that much. That's called the activation energy, is like the energy needed to activate it. So that would be A. And that's it, isn't it? Okay, so that's that. Right, I'm moving on to three because there have been. Oh wait, yeah, moving on to three. Right then, one BI four. Do you mean three? One BI four. Don't know what that means. One BI. Let's do that one. Um, Tell me if there's anything else, but I won't do that because I just did that. Oh, this must be it. One BI. This one. Right. For a reaction, the value of A is 1,370. So they're saying that A is 137. This is a bit of a logical question. 1370. C is 3230. What is B? Well, if you imagine this was like a maths question where I told you that the length of this line is 3230, and then the length of this line is 1370, and I said to you, how long is the blue line? That's effectively what this question is, which is saying to you, well, what must B be if C is 3,230 and A is 1,300? You just take them away and you'll be left with the answer. Should be it. Um, right. I moved on from booklet two. I need to ask the question at the beginning, please. Right. So that was that. Where else were we? For 5AB. Right. There's a really tough question than this. A student burned four fuels and compared the amounts of energy they produced. Okay. Heat produced when each fuel was burned was used to raise the temperature of 100 grams of water. The student noted the mass of fuel burned, the ingredient temperature, and where the flame was smoky. Right. So we burned these different fuels. This is how much of each fuel we burned. This was the temperature change, and this is whether we got smoky or not smoky flames. They suggested the vegetable oil was the best fuel for producing heat. Why? Because you see, look, we only burned 1 gram of vegetable oil and we got a 15-degree temperature increase. Whereas in all of the others, you see, look, we needed 2 grams to get 20 here. So in other words, we times by 10 here. So each gram gave us 10 degrees of increase. Here, each gram gave us 3 because 3 times 3 is 9. Here, each gram gave us only 6 degrees of temperature increase. If you're trying to produce heat, you want to produce a lot of heat with a small amount of substance. Here, with 1 gram, we get an increase of 15. So the way to answer this question would be, well, I don't know, I'll have to check, would be to say that um, 1 gram of vegetable oil gives a 15 degree C temperature increase. Okay. And explain that for all the others, there is a lower increase per gram of fuel. So there's a little bit of maths to do in that question in doing these things. Um, yeah, I'm going through booklet three. Okay. So just an environmental problem that could be you. I will get to that question six that you said on booklet three. Um, Right, we're trying to find the list of questions. 5A, B, 6, 1, and 2. This is 5, A and B. Environmental product will be called when large amounts of vegetable oils are burned. Okay. Uh, Probably, I mean, the easiest answer with burning any fuel is to say that it releases carbon dioxide, which can cause global warming. And then it also says how it could be overcome. A sensible way to overcome too much carbon dioxide. I mean, there's lots of answers, but I think the simplest one is to plant more trees. Because, if we're burning loads of fossil fuels, but we're planting trees, then the trees, remember, take in carbon dioxide from photosynthesis. So it makes it a bit easier. Six, part one and two. Describe activation energy. Okay, so there should have been a definition, it is the energy needed to start a reaction. I think that's the easiest answer. It activates the reaction. Explain why the reaction produces molten iron. Don't know. So there's molten iron liquid. Um, Explain why it produces molten iron. Um, okay, that's quite a hard question. So you probably want to say is that this graph, and you should know this, shows an exothermic reaction. Okay, so the reaction is exothermic, and if it's exothermic, it means it releases heat. And if heat is given off, that can explain why something melted. Okay, so what we might have done is the heat being given off resulted in the temperature being higher than the melting point of iron. The reason something melts is because it gets hotter than its melting point. Okay, that's six. 2, 7A, 7D, 7E. Three improvements to investigation. I'm just going to read them out rather than write all this down. Whenever you're doing any investigation involving a thermometer that you're trying to measure temperature, there are certain things you should do. You should not use a metal container. You should use a polystyrene cup because they are better insulators of heat. We're trying to keep the heat in as much as possible so that the thermometer records it. Use a polystyrene cup. We should also put a lid on it. Put a lid on it. And also, if we look at this thermometer, you should know that there are better thermometers than this nowadays in 2026. We do not need to use a thermometer that does this. We can use a digital thermometer that gives you a more precise, accurate number when it comes to thermometer. So they are your three improvements. Um, 7A, you don't need to do B, 7D, and 7E. Um, right, gradient of a line. This is more of a maths question. What you need to do is to work out the gradient of a line, you work out how far up you've gone. So from 0 to 50, that looks like. And how far across you've gone, that is 0 to 6. And you do 50 divided by 6, and that would be the gradient. Why should you not use more than 10 grams of zinc? Right, if you use 10 grams of zinc, it's going to get really hot. And I suspect it will be quite dangerously hot. Let me see what the mark scheme says. Yeah, it'll just be too hot. Yeah. So look, this little graph only goes up to 6 grams, but you can assume that you should draw this line, by the way, that at 10 grams, you're going to get an 80 degree C temperature change. It's going to be too hot. Okay, and you've got to extend the graph line anyway for that one. Right. Does that answer most of booklet 3? Yes. Yes. Um, Sorry, 6I was the energy. So I'm using a really little pen. It's really hard to write. Energy needed to start a reaction. Write that a bit more neatly. Right. And I will just go back to one more question. 6A part one in booklet two. Okay, I did answer this question actually, but if you are showing that something is exothermic or endothermic, remember these words are to do with temperature. So if I'm trying to show that a reaction is exothermic, I would, how can I show that something has got hotter? You measure the temperature before the reaction and then measure the temperature after the reaction, and you see if there's been a change, and that covers it. Um, I will do one more question. 3C, booklet three, if I haven't done it already. Um, I'm not. Um, energy produced with hydrogen peroxide decomposition of hydrogen oxide. Stir the. Why did they stir the mixture? I think it's to make sure that it all reacts. Why do you stir, like, I don't know, sugar into tea? It's to make sure that it all dissolves. I assume that's the answer. That's why you stir things. The biggest error is how you can change the apparatus. Again, same thing. Beakers are generally made of glass. We should not use glass beakers in an experiment about temperature because a lot of the heat will go out from the bottom or the side, and this thermometer will not record it. So you're going to be getting wrong results, won't you? So you should use a polystyrene cup. When hydrogen and oxygen in water, how and how is it not? Well, okay, the answer to the final question, which is, so somebody's asking, which is a very valid question, which is when you react hydrogen and oxygen together, why is it water and not hydrogen oxide? And my simple answer to that question is it is hydrogen oxide. Water is just a common name for hydrogen oxide. When you go to the shops, you buy bottles of water, but really what you're doing is buying bottles of hydrogen oxide. They are basically the same thing. I'm not going to do 5C booklet 2. So that is the end of that. Once again, the person who's asking the question about booklet 2, what you really, really, really need to do is ask these questions all at the beginning, and then I will do them. But my fear is that you are doing the booklet as I am doing this session, which is not the purpose of it. So ask the questions at the beginning, and I will get to them as I did with everybody else who asked the questions at the beginning. Um, for 1A, is water or hydrogen oxide? Oh, I don't know. I don't know. Um, I'll tell you what the mark scheme says. You ready? Let me show you what the mark scheme says for that question. I suspect I will be right. Often there are more than one valid answers to questions. Look at that. You can write water, you can write H2O, you could write hydrogen oxide because they are the same thing. Steam is just another common word for water vapor. So these are all valid. There's not always, and this is why I'm looking at mark schemes are so valuable. There is not always just one answer to a question. Um, okay, right. Let me just answer your final question. I accept your explanation. 5C, booklet two. Um, That's a good, yeah, that's fair enough. That's a quite a hard question, to be fair. The answer is, right, let me just give you a very quick explanation before I quickly grab a coffee before I do the next section. This is very hard to explain, but on the left-hand side of a chemical equation, what we do is we break everything apart and then we make new stuff with it on the right-hand side. So the reactants in a chemical equation are broken, and then we make new things. I know you don't think of it like that, but that's actually what you're doing when you react things together. You're breaking stuff and then you're making new stuff with it. So all the breaking happens at the beginning. So essentially, you put an X there. Um, what is the best way to study efficiently? This is a good way, I imagine, is asking questions and doing things. The notes that we recommend that we give you, write them. You can actually find very, very good quality videos on the internet about a lot of the stuff that you need to learn, including the ones that we have that you have access to in theory. Um, and but yeah, everybody's slightly different when it comes to how you revise or study. But can you find this on YouTube? This today's session? Yes, you will be able to. It will just be it goes on there about half an hour after I finish, I think, when I finish at about 9. So it takes a little while to get there. So yes, you'll be able to watch this back should you wish to. But what I can do with you at some point is I will get in touch with you separately, the person who's asking the questions about studying, and we will have a little chat about it in due course, and I will might do a separate meeting with you and talk about it. Right, I'm going to go and be back in 5 minutes. Right, hello. Two chemistry topics that we did this week, which were, well, rates of reaction and energy changes with year 10. And then we did some reversible reactions as well. Um, we have some questions from the year 10 booklet. Let's go. Three. Right, I'm going to have to read it all just quickly just to make sure I'm understanding what's going on. Temperature change, fine. Raw graph, fine. Um, ugh. Right. Students used to place copper, iron, magnesium, zinc in all of the reactivity metal in this reactivity series. Right. It's got to be displacement, hasn't it? Um, okay. Let me work out how to do this. The easiest way, let me see, there's more than one way, so I'm trying to decide what the easiest way is. Right. If something is more reactive than something else, if we're focusing on the fact that, well, in fact, we can literally read the first line here. The temperature change depends on the reactivity of a metal. So if a metal is more reactive, we would get a bigger temperature change when we react it. So for example, what we could do is react each of these metals with something. The something can be an acid. It's an easy way to do it because acids react with everything essentially. So what you could do is add all the metals separately to a fixed volume and concentration of an acid, like hydrochloric acid, for example. Okay, so we're going to do that in probably a polystyrene cup. So here's a polystyrene cup in a polystyrene cup. Okay, so here is your acid, fixed volume, fixed concentration. You add a metal into it, you will have a thermometer ready to go. You will measure the temperature change or measure the highest temperature that it reaches. So it's going to give off heat and your temperature will increase. And what you should find is that the most reactive metal results in the highest temperature change. And then you can figure out, therefore, based on your unknown metal, where it would fit, right? Because whatever its temperature changes should fit in it. So, for example, let's say one of them increased by 20 degrees and then one of them increased by 18 degrees and one of them increased by 12 degrees, one of them increased by 9 degrees. And then you have an unknown metal that increased by 15 degrees. You know it fits in there in your reactivity of each metal. So that's a sensible way to do that question. 1B, I'll just go back to that in a second once I've done 3D. Draw a fully labeled reaction profile for the reaction between zinc and copper sulfate. Well, I mean, where does it mention what zinc and copper sulfate is in here? Um, well, look, when you reacted zinc with copper sulfate, there was a 17-degree temperature increase. There was an increase in temperature, which means it's an exothermic reaction. So all you need to do is draw one of those reaction profiles for an exothermic reaction. Um, and this is how you do it. Remember, there's only two of these diagrams. Either it goes like that, which is exothermic, or it goes like that, which is endothermic. So if it's gone up in energy, it's endo. If it's gone down, it's exo. So something like that. There you go. Something like that. But then we've got to label it. The way you label these diagrams, there's usually four labels. This section here is the energy of the reactants. So what we begin with. Where we finish is the energy of the products. The difference in the height here and here is the overall energy change. So it's gone down, hence exothermic. Um, Sorry, yeah, it's gone down in the sense that the amount of energy we began with is more than what we finished with. So that extra energy has been released to the surroundings. Um, and then this here is called the activation energy. We have to increase the temperature or the energy to begin the reaction to get it going. And that covers that one. Right. And then someone, also changing if we want on from, do I know any resources? Yeah, the videos that I made. Message us separately somewhere and we'll make sure that you have access to them. 1BI. Right. Bond energy calculation, my favorites. So, tricky question this. Use the bond energy to help you calculate the energy change for this reaction. Right. In to keep it simple, to work out the energy change in a reaction, you have to work out the energy that you have on the left-hand side. So that is before the arrow, all of that stuff. Um, And remember, just to go technical into this, what we're doing on the left-hand side is we're taking in loads of energy to break all of these bonds. We're trying to break everything. So we suck in energy to break all of the bonds there, and I can work out how much energy that would require using the numbers in this table. So it's very hard to do this because it's so spread out. But on the left-hand side, we have got this CH bond, another CH bond, another CH bond, and another CH bond. So there's four of these. But there is also a two here to show that imagine this diagram was drawn twice. So effectively, there's eight of these there. So eight lots of 435. That's how much energy we're going to take in. We're also going to take in enough to break this OO bond, which is worth 498. So on the left-hand side, we will need to bring in 8 times 435 plus 498, that much energy to break everything on the left-hand side. Then, on the right-hand side, we release energy when we're making all of these bonds. So we're making new bonds with all of those pieces, and we're going to release energy when making those. Okay, so it's going to give out energy. And again, these numbers are the same. We just need to figure out what we've got here. So we have got CH, CH, CH. Okay, so that's three of those. So 3 times 435 plus a CO, which is 805, plus an OH, which is 464. But there's a 2 in front of all of this. So the whole thing that I just did is doubled as if you got that drawn twice, times 2. So that means we are releasing 5,148 energy um, when making the new ones. So I'm going to put that as a minus because that shows that we're losing that energy. We're gaining this energy and losing this energy. The difference between these two, so 3,978 minus 5,148, is the overall energy change. So we bring in this much, but lose that much. So overall, we lose 1,170. That would be the answer to that question. To make sure that is the answer to that question. Yes, it is. Okay, let me do 5 part 2. Did I do that? Okay, quite a hard question this, but by part 2 says there's a reaction here that produces molten iron. So we're producing iron, but it's a liquid, which is unusual. It's very, very. How do you get something to melt? Well, you make it really, really hot. What does this reaction show you? It shows you that we have got an exothermic reaction because the amount of energy has decreased, so we must have lost energy to the surroundings. So explain why it produces molten iron. You need to explain that it's an exothermic reaction. So energy or heat energy has been released or given off. And then how do you make this melt? Well, we must have made it hotter, or the temperature must have been higher than the melting point of iron. That's why it melted. And that is that. Um, I have a question. You are welcome to ask the question. Um, I've got two, 6A and 6 somebody else asked as well, didn't they? 6. Okay. Ooh, ooh, mm. Okay, right. Number 6 says methane and oxygen react together to produce carbon dioxide and water. Okay. Um, and it also tells you that this much energy is given out to the surroundings, so it's an exothermic reaction. The methane gas will not burn in oxygen until a flame is applied, but once lit, it continues to burn. Right. It's quite hard to explain this question, but as I said, in any chemical reaction, what do we need to do? We need to break the bonds on the left-hand side first, and then it will start turning into the stuff on the right-hand side. So why must energy be supplied to start the reaction? Let's explain that first. We need to break the existing bonds on the left-hand side. Or you can say the reactants. So we have to break those first, right? Um, Molecule and molecule react when they collide. Right, that's the first thing. Then, so that gets it started. But then, as we're making these two, energy is given out, right? Because that's what happens when you make new bonds, energy is released. And crucially, um, but actually, no, I want to say more energy is released when making new bonds. Because it tells you in the question that overall we get 818 given out. So there's more released when making new bonds, um, and this extra energy that's being released continues to break the bonds on the left-hand side. So we only need to supply the energy at the beginning once, then we can carry on using the extra energy that's being released to keep it going. That's why, essentially, to light a fire, you do it once and then it keeps on going. You don't keep on having to sort of heat it up. It's because the existing heat gets reused essentially. So this extra energy, sorry, I'm using a very little pen, so it's quite hard to write. This energy breaks more bonds, so the reaction continues. Something along those lines would be sufficient for that. Let me read this question. Biology notes. Yeah, I will give them to you when I see you. I'm not sure why that happened. How do you define exothermic and endothermic? Exothermic reactions release energy to the surroundings. Endothermic reactions take in energy from the surroundings. Um, will we have this recording before class on Saturday? Yeah, it goes straight to YouTube in about an hour. So yeah, yeah. Um, right, question. I'm sorry, getting to 6B, sorry. Right, sketches indicate the diagram, the net energy released. Okay, so it's an exothermic reaction once again. So we need to finish lower than where we started. That's the first thing. Um, and then what we need to say is the net energy released is the difference between these two. That's the energy released. I think that's all you need. Yeah, that's it. That's all that is. It's just any typical one of those diagrams. Um, 6B done. Uh, will that cover everybody's questions apart from 7 and 9? Yeah. 7. Decomposition of water. Here's an energy level diagram. Ugh. Explain the significance of X, Y, and Z on the diagram. Right. X is the activation energy? That's the first thing to say. Remember, from the beginning to the top is the activation energy. This is the energy. You've got to add some detail to this answer. It's quite a lot, right? This activation energy is the energy needed to break the bonds. Okay? That's what you have to take in this energy to break the bonds on the left in the reactants. Okay. Then from here, we now release this much energy, right? So from the highest point to what goes down now is the energy being released. So Y shows the energy that is released. And when is energy released? It's when we're making new bonds on the right-hand side. Okay. And then the difference between those two is what Z is. Z is the overall energy change. So we've taken in this much, we've released this much. Okay. And the Z is the difference between the two, which you can actually calculate if you want to get some more marks, because it's 1856 minus 1370, which is 486. Um, and that's probably it. So you could probably add one more thing, right? The fact that we've overall added energy shows that this is an endothermic reaction, which you should be able to tell just by looking at the shape of the graph anyway, because, as I said, if this line is higher than this line, it's endothermic. If that line was lower than the first line, then it is exothermic. Um, right, that was that one. Nine was another question. Which chemical bonds are broken and formed during this reaction? There's an arrow missing here. There should be an arrow there. So, I mean, all broken bonds are the left-hand side. So methane and oxygen and are broken, and carbon dioxide and water are formed. Is that the answer to the question? Um, oh, there's more detail to that. Whoops. So specifically, right, that's quite a difficult question, actually, specifically. Um, okay, that's quite a hard question, but I shall tell you that on the left-hand side, um, we have these CH bonds that get broken. We also have O bonds there, the O2 is quite a hard on this. These are broken, so you can mention that they are broken on the left-hand side. And then formed on the right-hand side, we have CO bonds, it's carbon and oxygen, and H and O, so OH bonds. These are all bonds that are made on the right-hand side. And then that is question 9B. Did I do that? I mean, I won't do 9B because it's essentially the same as that earlier question. X is the activation energy, which is the energy taken in. Y is the energy released. And Z is the overall energy change, which shows that this is an exothermic reaction because we released Y, which is more than X. That pretty much covers it. Um, and then the table on question 8. Ooh. Right. A lot of counting, basically. Right. Firstly, bonds broken are always the left-hand side, and bonds made are on the right-hand side. So that's the first key bit to get right. Um, what is the R? Where's the R? Sorry, is that in question? Um, sorry, let me just go to that quickly. Oh, sorry. There's a mistake in the printing. I believe that should be like an arrow that you have in the middle of an equation. Something's gone wrong with that. So that should just be an arrow. I don't know why there's an R there. Apologies. Um, right. Counting. On the left-hand side, how many CC bonds are there? One, two, don't see any more. But because of this two, there's everything's been doubled. So there's four. Okay. CH bonds. One, two, three, four. And then this two doubles everything. Eight. OO bonds. There's one there, but then there's seven of them. Seven. CO, none on that side. And HO, none on that side. Okay, so on the left-hand side, there's none of them. On the right-hand side, CC, do we have any CC? No. Um, do we have any CH? No. Do we have any OO? No. Interesting. CO, we've got one there, another one there, two, but then they've been quadrupled, which makes eight. And then HO, one, two times six, 12. That should be the table. Got that right. Oh God, the mark scheme looked really wrong here. Um, I've miscounted the CHs, haven't I? Yeah, that's right. Sorry. One, two, three, four, five, doubled is 10. Apologies. Yeah, there you go. Sorry. Just a long day. Um, right, so it was 4, 10, and 7. Is that all right? Are we happy with that? Okay. Is that enough? Right, is that all right? Anything else? Anything else on these booklets? Anybody? Okay, I have been asked a couple of other things. Um, Paper one chemistry, AK triple sum, what do I ask? If I asked for a specific question from a past paper, would you be able to do it? Yes, is my answer to that question for now. So if you had a specific question from a past paper, then I will try and find it quickly and go over it. In the meantime, I received a maths question, which I should just get out of the way now. Um, Let me just get it open. Loading. Sorry. Question 7 on the higher paper for chemistry, AQ triple on the higher paper 20. Yes, I'll come to that in just a moment. Right, I had a math question, which was, I mean, there's no easy way to explain this other than you just have to do the work, which is, um, let me see if I can get it in here. Does that work? Oh, it does. Okay, I'm just going to answer this question, then I'll move on to that chemistry question. Appeared. Um, so, two people make sequences of numbers. The first term of both sequences, we've got Sarah, we've got Tom. First term of their sequences is 10. I should do this, in fact, no, I want to do this like this. Here's Sarah, here's Tom. The first term is 10 of both of their sequences. The term-to-term rule for Sarah's sequence is add 10. So we keep adding 10 here. So it goes 20, 30, 40, 50, and so on. For Tom, we add 35. So 10 add 35 is 45. 45 add 35 is 80. 80 add 35 is 115. Is that right? Yeah. And 150 and 35 is 150. I'm going to stop there for a moment. The question says, each sequence stops when the term reaches or above, goes above 500. Find the number of terms that are the same in both sequences. The number of terms that are the same. There is no really quick way to do this, except for realizing that the only numbers that are going to be the same in both sequences are the multiples of 10. Because the first sequence is just all multiples of 10, isn't it? 70, 80, 90. So, for example, that is a term that's in both sequences. That's going to be the same in both sequences. That's going to be the same in both sequences. So, in other words, every other term in Tom's sequence is going to be in Sarah's sequence because of the fact that it's a 35. So 35, if you add 35, it won't be in the sequence because it ends with a 5. But if you add another 35, you'll get to a multiple of 10 because it'll end with a 0. So what I can do quickly now is rather than keep adding 35, I'll just keep adding 70 because that's two lots of them because each of those numbers will be in Sarah's sequence. If I add 70 to this, I get 220, then 290, then 380. If I got that out right, I feel like something wrong. No. Add another 70 and I get 450, I think. I hope I've done that right. And then if I add another 70, it goes to 520, which goes above 500, so we don't go there. Let me make sure I've done that right. 70 is 150. 150 add 70 is 220. 220 add 70 is 290. 290 add 70 is 360. There you go. I knew I'd done something wrong. Okay. 290, yeah, 360, add 70 is 430, that's 500. So I didn't really need to do the middle 35s, if that makes sense. So now this one, two, three, four, five, six, seven, and eight. These eight numbers will be in both sequences because they have to be. Um, I thought about, so the question is there no easy way to do it with algebra? I don't think so. I might be wrong, but I don't think so, only because with algebra, you're not going to be able to find out the number of terms that are the same in both. I don't think you can get to that. So you can get to a number that is the same in both sequences, possibly. But to get to all of the numbers that are the same in both sequences, I don't think it would work. So I think that is the way to do it. And also, it is not particularly long. It's taken me about what, 30 seconds to do that. So understanding that if you keep adding 70, so two lots, every two jumps is a multiple, is going to be the same in both sequences because it'll end with a 0, is the way to do that. Unfortunately, I can't think of a quicker way to do that. I did try an algebraic way to start with, and I realized that it's probably just quicker just to do this. Right, I will do a chemistry question that has been asked. Question 7 on the higher chemistry paper, AQA triple science. Oh, jeez, I'm going to find that now. Um, Let me find it. Twenty-one. 2021 was weird, wasn't it? Because it was November. Odd. Um, okay. Okay. Right. The answer to the first question. So, the key difference between electrolysis and a chemical cell. Think about what a cell is, a cell or a battery in physics. What are we trying to do with a cell? Can I write on here? I can't write on here. Let's put it over here. Right. If I've got a circuit, what's the purpose of this cell? It is to essentially produce electricity so that I can power my toys, as it were, or charge my phone, or turn my phone on, or whatever it might be, right? That is the point of a fuel cell. The whole topic of fuel cells is you're trying to produce electricity using a chemical reaction. So you produce in the battery, there's some chemicals, they kind of react together and they produce electricity. So let me put this over here. The difference between electrolysis and a chemical cell. In a chemical cell, we use a chemical reaction to produce electricity. But that's not what we're doing in electrolysis. In electrolysis, we're almost doing the opposite. We're using electricity to produce a chemical reaction. And that chemical reaction is like the splitting of the compound. That's the whole point of electrolysis. You've got a compound and you're trying to split it up, and you're using electricity to do that. You're using the fact that we've got a positive and a negative electrode, and we can split the ions up in a positive and negative direction. Do you see what I mean? So that's the key difference between the cells that are using a chemical reaction to give you electricity and electrolysis that's using electricity to give you a chemical reaction. Essentially, there's two-way around, two ways around. Right. This requires some explanation, quite a long explanation. But I will do it. Right. Firstly, let's talk about the electrolysis of molten lead bromide. Lead is, I don't know where it is. I think it's in group. I want to say group two. I don't know. Anyway, it's a 2 plus ion. Bromine is in group 7, so it's a 1 minus ion. Right. Molten lead bromide. If I melt lead bromide in my electrolysis thing, okay, positive, negative, then in my electrolyte, I have positive ions from the lead and negative ions from the bromine. I have nothing else. That's really important because if you do a aqueous solution or of a compound, then there's water in there as well, and it complicates things a little bit. In this case, because I've only got positive and negative, the positive ion will go to the negative electrode and the negative ion will go to the positive electrode. And they've asked you to complete the half equation for the production of bromine. So what's going to happen here is that we will get bromine being produced. Here we will get lead being produced. The way to do this first, and if I just go away from this in a minute, this is how I explain half equations. I say that I start with this ion and finish with the atom or the element on its own without the charge. That's the whole point. We're doing ionic bonding in reverse. In ionic bonding, we have atoms that become ions, then they join together. In electrolysis, we have the ions already, and we're turning them back into what they were to begin with. So the way to understand this to start with is to say, well, if I've got a negative ion, how did it become a negative ion in the first place? How does bromine become a negative ion? It gains one electron because electrons are negatively charged. So if we're going backwards from here to here, surely we need to lose one electron. And that's what we do. I'm going to put a minus an electron here to show that I have lost it to then go back to what I started with. However, with certain compounds, especially all the group 7 ones and hydrogen and oxygen, they come off as a diatomic molecule, which means there's a 2 after them. If I put a 2 after this, what I now have to do is balance it by doubling that. But now I've got 2 of these ions, so each of those should lose an electron, so I'd have 2 of them. That would be the half equation. But annoyingly, with half equations, when you have a subtract in them, we don't like having negatives in a chemical equation. You never see it, right? It's not something minus or something. So what we do, like a maths equation with an equals, we move the minus to the other side and add it. So it's just that way it looks how they want it to look. And that is essentially the answer to the question above. You'd put a 2 here and a 2 there. That is how you'd go about doing that particular question. Um, oh my goodness. Right, okay, sorry. 2 aqueous salt solutions are electrolyzed using inert electrodes. Complete table will show the product of each electrode. So tricky, that isn't it? Water and oxygen. Oxygen. Um, okay, right. It's a very small number of marks for a lot of understanding of electrolysis. In electrolysis, when you have solutions, it means you've got H plus and OH minus ions in there as well as the ions from these. So we've got copper ions and nitrate ions. Nitrates are, it doesn't matter what they are, but they're negative. Um, in this scenario, when you have 2 positive and 2 negative, the rule is that of the 2 positive ions, the less reactive one goes to the negative electrode. Out of copper and hydrogen, copper is less reactive. So copper gets produced there, which is why they've already filled that in for you. Of the 2 negative ions, the rule is that if you have an OH minus ion, which you will if there's a solution, that one goes. Oop, pen's gone. Give me a moment. No. Yeah, that one goes unless the other ion is a group 7 ion, like bromine or chlorine. In this case, nitrate is not one of those, so that doesn't go. The OH minus ion goes. The product of an OH minus ion is, I mean, it's actually two. It's water and oxygen, but oxygen is the answer to the question. So oxygen is what's produced at the positive electrode. Right. If we did the same thing with potassium iodide, right, solution again. So we've still got H plus and OH minus. We've now got potassium ions and iodine ions. Of the 2 positive ions, the less reactive one goes to the negative electrode. Out of potassium and hydrogen, hydrogen's definitely less reactive. Potassium's in group 1, very reactive. It is definitely more reactive than hydrogen. So hydrogen was going to go to the other one, negative electrode. And we're going to get hydrogen gas being given off here. Hence, the product at the negative electrode here would be hydrogen. Of the 2 negative ions, the rule is that the OH minus ion goes to the positive electrode and produces oxygen unless the other ion, the other negative ion, is a group 7 ion. And guess what? Iodine is a group 7 ion, which means that's the one that's going to go to the positive electrode, resulting in iodine being produced at the positive electrode. It's about knowing the rules of electrolysis very, very well, especially when, well, only when there is a solution involved, because it just messes things up in terms of what happens. Right. And then we've got a lengthy question now. Where is it? It's only worth 4 marks. Right, what are we doing here? Electrolysis of copper nitrate solution using inert electrodes. So in the copper nitrate, we already understand that we get oxygen and copper being produced at the electrodes. Um, current. We weighed the negative electrode. They wanted to investigate how the mass of copper produced at the negative electrode varied with time and current. They weighed the negative electrode. So what happens during this electrolysis is this copper that I demonstrated here. I mean, copper's a solid, so what it actually does is it plates the electrode. So the electrode kind of gets heavier as time goes on because it ends up on the electrode, quite literally. Um, so they weighed the negative electrode, set up the apparatus as shown in figure 4. Adjusted the power supply until the ammeter shows a current of 0.3 amps. Switch off the power supply after 5 minutes. Rinse the negative electrode and allow to dry. Reweigh it, and then repeat 1 to 6 for different times. So they might have done it for 5 minutes, done it for 10 minutes or whatever. And then repeat at different currents as well. Some of the copper produced did not stick to the negative electrode, but fell to the bottom of the beaker. Interesting. So here is the copper. Some of it fell off and was down here. So that means that when I weigh the electrode, it won't be on it. It won't be part of my calculation, but I need it. How could you do it? Well, surely what I could do to try and get hold of that is, because remember, we've got a solution down here with some solid stuff in it. How do you remove some solid stuff from a solution? Filter it out, firstly. Then you probably want to dry this, because remember, you have to dry things when everything's wet, because otherwise you will weigh the water. So dry it so that there's no excess water on it. Then weigh the copper collected, and then add it to the mass of the electrode that you worked out earlier. It's a really unusual question, but essentially we're saying we've dropped some of it, so how do we add it in? So you have to go through the process of explaining how you would do that. Right, was there more? Um, the students plotted their results on a graph, and they found that at 0.9 amps, you got more copper produced than you did at 0.6 and at 0.3. And then these are the times as well. Okay. Um, They correctly concluded that the total mass of copper produced is directly proportional to both the time and the current. How do the results support the conclusion? I think it's just a straight line, isn't it? Um, there's a straight line through the origin, basically, that proves that as one like doubles, the other doubles, which is what proportionality is. So the key is the straight line part of that. Um, how do the results done that? Oh no, sorry. How do the result? Oh God, wait, hang on. Different questions. Time. Okay, that's the for a given current, straight line through the origin. And then how do the results support the total mass produced direct proportional to the current? So to the time, okay. Yeah, the easiest way to answer part 7.5 is that as time for any given current, as the time doubles, the mass of the copper produced doubles as well. So you could get some measurements in and say at 10 minutes we got this much copper, at 20 minutes we got twice as much at the same current. So that proves that it is proportional. How do they support the conclusion that the is directly proportional to the current? So for the current, um, what you could do is compare 0.3 and 0.6 and say, well, at 20 minutes, at 0.3 amps, we produced this much copper, but at 20 minutes for 0.6 amps, we produced twice as much. You'll find that the measurements work if you do it like that. Um, God, how long is this question? Right, 7.7. Copper nitrate solution is blue. Suggest why the blue color fades during the electrolysis. Right, again, it's quite a tricky one, but it's to do with you are meant to know that copper ions create blueness, essentially. And at the beginning, oh, sorry, let me go back to my beaker. The copper nitrate solution, which is here, right? Let me try and tidy this up a little bit. Okay, copper nitrate solution, which is here, is essentially blue because of the copper ions that are in here. But what's happening to the copper ions during this experiment? They are going to the negative electrode and they're being removed. If you're removing the thing that makes it blue, it's going to be less blue. Why does the blue color fade? Because the copper ions are being removed, or discharged is the fancy word for it. But if you just say removed, then that would be fine. Um, oh God. Um, Number of atoms of copper produced when copper nitrate solution is electrolyzed for 20 minutes at a current of 0.6 amps. Okay. So let's go to the 20-minute line at 0.6 amps and see what it says. 20-minute 0.6 is 0.22. Make sure that is correct. No, 0.24 is going up in twos. 2, 2, 2, 4, 2, 6, 2, 8, yeah, 0.24 there. Okay, so the mass of copper produced is 0.24 grams. Okay, the question is determine the number of atoms. Right, just as a quick reminder of your understanding of moles, okay? A mole is a mole because it is a fixed number of atoms. So if I've got 1 mole of carbon, I have exactly a certain number of atoms. If I have 1 mole of magnesium, I have exactly the same number of particles, essentially, the atoms. And that number is this number here. So 1 mole of anything is always this many particles or atoms or whatever you want to call them. So essentially, I need to figure out, given that I have 0.24 grams of copper, firstly, I need to figure out how many moles this is. Once I know how many moles this is, I can then times it by this number to figure out how many particles there are. Do you see what I mean? So if I had 2 moles, then it'd be this number times 2. If I had 4 moles, it'd be this number times 4 to get to the number of particles. So the first thing to do is to convert this mass in grams to moles. The way you convert grams to moles is that the number of moles is the mass in grams divided by the MR. In this case, 63.5 of copper. The mass in grams is 0.24. If you divide that by 63.5, it turns those grams into moles. And gives you a very small number, which I'll just leave on my calculator for now. And to now turn that number, which is the number of moles, a very small number, into atoms or particles, you now times it by this number. And that will give me a more reasonable looking number. Not much. Anyway, so they wanted three significant figures. So that is 2.28 times 10 to the power 21. That is the number of particles. So just to be clear, this Avogadro constant thing here is a value for how many particles there are in a mole. The whole point of using moles is it sort of equalizes everything so that if I've got 1 mole of something and another and 1 mole of something else, I know that the number of particles is exactly the same. And we care about particles because they're the things that get involved in a chemical reaction. Where did I get 0.2 from? I got it from the graph. So the question says, determine the number of atoms produced when copper nitrate solution is electrolyzed for 20 minutes at this current. And we had earlier on in this question a graph that had current and time and stuff on it. So we went to the 20 minutes and we went to the zero point 0.6 amp line and read across, and that gave us 0.24 there. Right. I think that's all I'm going to do for the time being. I think that was a heavy sort of question. Yeah, I don't know what we're doing next week. I have absolutely no idea. Physics required practicals, maybe. I don't know. Right. For year 11 and for everybody else, I can't remember. Right. I think that's it. If you have any other questions, use the WhatsApp and I'll get back to you. Otherwise, I will see you later.